Okay, so the next speaker is Rajamani Vijayaraghavan. Maybe I'm not sure my pronunciation is correct, but anyway, so he's going to tell us about a ring resonator-based coupler for dense long-range connectivity in superconducting qubit. So could you go ahead?
Yes, thank you for the introduction, and thank you to the organizers for this opportunity to present in this conference. As you can probably see from the title, and if you've seen the abstract, it's going to be quite different from a lot of the talks here. But I'm quite excited to tell you about this new work which we recently did in our lab at TIFR Mumbai. And this work was primarily done by Sumeru Hazra, who's the lead author on the manuscript, and supported by Anirban, both of them PhD students in my group. So just to really give a very, very quick introduction to this field of superconducting qubits. These are essentially electrical circuits made using superconducting elements like the Josephson junction, which is shown here as a cross. And here two of them shown together, which makes a tunable inductor. But because the Josephson junction is nonlinear, it's actually a nonlinear inductor, and typical values are shown here. And when you shunt it with a capacitor, you get essentially a nonlinear oscillator whose sort of classical dynamics would look like that of a pendulum, in the sense of it has the same nonlinear potential with a restoring force proportional to the sign of the displacement. So if one then considers the quantized energy levels in such an oscillator, which for us is typically in the few gigahertz regime, like around 5 gigahertz or so, then you can see that there are these few quantized energy levels within the well. And because of the nonlinearity, the transitions between the next nearest neighbor transitions are, the frequencies are no longer the same. And that effectively allows you to use the two lowest levels as a two-level system or a qubit, which is sort of the building block of any experiments for quantum computing or other quantum experiments, including measurements and other fundamental physics experiments as well. So there are many other ways of building superconducting qubits by combining these Josephson junctions, capacitors, and inductors. But this particular design of a nonlinear oscillator, which is also called a transmon qubit, is one of the most popular and the simplest design as well. And here's a typical image of such a device. You can see it's fairly big. Right in the middle is the Josephson junction, two of them in a loop forming the squid. And these big metallic pads here, which are all made out of aluminum, which is the choice of superconductor here, they serve as the two pads of the capacitor. So together this functions as an oscillator, a nonlinear oscillator, and hence a qubit. And we operate it at dilution Fritz temperatures, which is about 10 millikelvin. And the main reason here is that you want to suppress thermal fluctuations as much as possible and be in this deep quantum regime, so that you can prepare and control the states of this quantum system very precisely. Okay. Now, when one wants to do any experiments using these qubits, either for quantum computing applications or for, say, quantum many-body physics experiments, you need to create interactions between these individual qubits. In the context of quantum computing and algorithms, this coupling is what allows you to do entangling gates, that if you want to create entanglement between different qubits, then you need to have some interaction. And in superconducting qubits, this interaction is typically mediated by some other circuit element, say a capacitor in this case. And then, this now looks like two coupled nonlinear oscillators. So this is a very typical model which is used. And you can use a capacitor, which usually is done by just positioning the two devices next to each other. So it's sort of proximity coupled and typically leads to nearest neighbor kind of coupling. One could also use resonant cavities, and you will see some images in the coming slides. If you want to place the devices slightly further apart, and you can sort of imagine that that would be necessary if one is trying to build a multi-qubit kind of network. And then once you have this kind of a system, this coupling is sort of what we call the transverse coupling or dipolar coupling between, you can think of these two qubits as dipoles. And because you typically want the interaction to be off by default and only turn it on when you need it, This is often achieved by just keeping the systems off resonant rather than having some tunable device here, though that is also possible. And then you use the ability to tune the frequency, because this the squid allows you to tune the inductance. You can then bring them onto resonance when you want to do a multi-qubit, in this case a 2-qubit operation, or you can also excite them with appropriate microwave tones, which create an effective interaction in a dressed frame. And these are sort of the two typical approaches which are taken for doing entangling gates. And that's sort of a very quick introduction to single and 2-qubit systems. But then you would like to put these together, and here I'm showing some examples. This is now a fairly old design where you can see these linear array of qubits. Each of this plus looking structure is a qubit, and they are just arranged next to each other, so they have nearest neighbor coupling. Here is another design from the IBM group, which is more of a 2D planar design. And these red dots are the qubits, which in the image correspond to these little squarish things in the middle. And then now you can see that in the 2D grid, there are these squiggly lines, which are the resonators I talked about, which mediate the coupling. So it's fairly clear from this that you want to be able to connect the qubits with some resonator or a capacitor or some other device to be able to initiate a coupling so that you can do entangling operations between them. Okay. Now, this automatically shows you that there are sort of limitations on how the qubits are connected depending on how they are laid out. In contrast, even though in trapped ions, even though they are often an array of ions which are trapped in a linear fashion, by interacting with a common mode, which is a mechanical mode, they can actually create a system where every qubit can be made to interact with any other qubit in the system. And a couple of years back, they showed this for about 11 qubits from the startup company IonQ, which actually was started by some of the leaders in this field. So we have been trying to address this problem in our own way and to sort of create superconducting systems which have this property of high connectivity. And the motivation is simple. Currently, all the processes are prone to decoherence, which means that the qubit states decay over some characteristic time scale. That just translates to a lot of errors when you introduce an algorithm. So you want to keep your algorithmic execution time as short as possible compared to the decoherence time. And this means that the more efficient the algorithm is in the sense of the number of steps you need, the better it is. And that is what the connectivity does, because if you want to do gates between long distance qubits, then you need to typically have more steps. Okay. Just a quick
sorry, Vijay, just one question about the previous slide. So in this ion case, the fully connected qubits, the connection becomes weak, very weak as you go further and further, or how is it?
No, so that's the thing. The distance actually doesn't play a role, if I understand correctly, because they're all connected to a mode, a mechanical mode of the oscillations of the, the string of ions. It's like a mass spring system, and they all couple to it, and they have to play some tricks to keep the coupling same, but there is some variation. And you will see that there are similar things which happen in the system, and how we have attack that particular problem using our idea.
Okay, thanks.
So just a quick aside, and also a little bit advertisement of some of the work here. Just in the same goal of having a connected network, we initially were looking at different qubit designs, and this is basically a more complicated oscillator network with more junctions and more capacitors, and it looks like this. And instead of creating one nonlinear oscillator, we basically create 3 coupled nonlinear oscillators, and that essentially gives you directly a coupled 3-qubit system as opposed to 3 individual qubits which then have to be coupled. There are pros and cons of doing that. You have to really think of this as a 8-level Hilbert space, if you like, as shown here. And then we showed that in a system like this, you have these 12 different transitions which are marked here. And you just have to send microwave pulses to these 12 different transitions, and that allows you complete universal control over this 8-level Hilbert space. So essentially, which means you can execute any algorithm or any Hamiltonian. And these consist of these native, what we call control rotations, in the sense that these are no longer operations on single qubit because they are all coupled together. These are sort of eigenmodes of the coupled system. So in the standard language, you say that, okay, this is a conditional transition on the third qubit, the green one, then the other two qubits are in 1, 1. And similarly, there are 12 of them. And then there are also these what we call virtual gates. Essentially, you just change the phase of your reference system, and that allows you to gates. And then we demonstrated that this allows you to implement your algorithms more efficiently because things are strongly coupled. It's a combined system. But then, you cannot also decouple them very easily. So this was one approach. And then we started thinking about the layout of the qubit itself. So here again, I go back to this layout. Now here a slightly bigger number of qubits shown here from an IBM design and a Google design. And you see that here is just a simple network 2D. Here there is some slightly more interesting choices made in terms of how the qubits are laid out. And this is a side point. I will come to it towards the end. In fact, IBM has gone to an approach where they've actually reduced the connectivity between the qubits, whereas what I'm trying to motivate here is that more connectivity is good. I will briefly talk about this, why they have done that towards the end of my talk. And again, the point is that they are, the coupling is typically nearest neighbor. And if you want to do gates between, say, two qubits like this shown here, you might have to go through several intermediary qubits, and there's no direct connection between them. So which means more steps, which means more time, and hence a likelihood of making more errors. So is it possible to have a layout which is 2D, but yet have the ability to have qubits which are not in the proximity to be coupled to each other and to be able to, we can turn on interactions between them. The ion trap approach is one where you have sort of a common mode. And this is somewhat, looks similar, but it's actually not. And I'll show you what the idea is. And the point is that even if you wanted to physically make connections, to be able to connect too many of them is going to be a big mess. Like, you cannot really do it in 2 dimensions, and then you have to do crossovers in 3D. Lots of technical challenges if you want to really increase the connectivity, but by adding physical connections like resonators between all the qubits you would like to interact with each other. Okay? Other people have done a few things to create highly connected networks. And one sort of very simple, obvious approach is that, okay, don't put only 2 qubits next to each other, put many qubits next to each other. So here was one example where they put 5 qubits, 6 qubits on one end of a resonator and 6 qubits on another end of the resonator. The resonator provides coupling between these 6 and those 6, but just the proximity of these qubits next to each other gives you the coupling to each other. And this was demonstrated, and they had to tune the couplings very carefully. But the net result is that for a small number of qubits, it's possible. Say they showed it for about 10 qubits or so. Maybe 10 to 20 qubits. But typically what will happen is that the coupling strength between different pairs of qubit was sort of represented here by these lines and different colors will vary a lot depending on where exactly they are positioned. And then they could also be non-uniform unless you specifically engineer. So then you have to worry about what is the coupling of this qubit to that node and this qubit to that node and so on and so forth. So for small number of qubits, this seems okay to do. And there was a very nice experiment here where they showed a many-body quantum evolution in this reference. But this is sort of not really possible to extend beyond maybe a few tens of qubits. And then the fact that the qubits are very close to each other physically would also lead to crosstalk kind of effects, which are problematic, because then you cannot drive one qubit separately from the other. So we started thinking about this, and we said, well, is it possible that your qubits are still physically spaced apart and yet have a connection which is non-nearest neighbor, and you can go further? And this was the idea we finally converged on. What you're seeing is here in green is a continuous transmission line which is sort of wrapped around itself. So this is what we call the ring resonator, because it's a resonant system because of periodic boundary conditions. So sort of you have to have integer number of wavelengths fit in that particular structure. And again, remember, all of these are at microwave frequencies. And then the qubits are connected to this particular ring along the circumference and then spread out uniformly. So this ensures that the qubits are spaced, so there's some physical distance between them. And then the question really is that, well, what is the coupling of this qubit to that versus to that one, and that one, and so on and so forth. And this is where it gets really interesting, is that what we actually get is that most of the qubits are actually coupled to each other. And the value of the coupling is quite uniform in the sense that we have only two different values, like a high value and a slightly lower value. And if the system is designed in a symmetric fashion, you will get a connectivity which looks like this. This is not all to all, but in this 12 qubit network shown here, each qubit is connected to 9 other qubits, and it's not connected to 3 of the qubits, two more qubits. Okay, and the actual design looks like this. So this is a piece made out of aluminum, and you can see this ring here in the middle. This is the transmission line which is wrapping around itself. And then there are all these chips, which are these transmon qubit chips, which are spaced. And on the outside, these little things which are sticking out, these are actually the measurement resonators. I haven't talked about that, but this is how you probe the state of the qubit by coupling it to another resonant cavity. So each qubit is actually coupled to 2 resonant cavities, one its own measurement resonator, and then a common, what we call a bus resonator or a bus cavity, which mediates the coupling between the different qubits. So how does this actually work? Okay, so to look at that, we basically consider this very simple model. Here is again a transmission line wrapping around itself, and you break it up into these 2 parts by just choosing 2 arbitrary points along the circumference of this resonator. And if the total length is L and this is small l, you have L minus L. And you can also parameterize these 2 points by the relative angle between the 2 qubits, which makes respect to the center. Okay. So this is now a very simple structure. It's 2 transmission lines whose lengths are different. And then you can basically calculate the scattering matrix of a structure like this. It's very easy to do in microwave packages. You can actually calculate this analytically also for such a simple case. And then we just model these qubits as linear oscillators just for computing the coupling, because that is a lower order calculation. So it doesn't matter. The nonlinearity doesn't give you much corrections. And then you just combine the system, and you basically get an effective coupled oscillator problem with some scattering matrix, which is defining the coupling. You solve for the normal modes, and from that you can compute the coupling strength between the 2 qubits. Okay, so we then do this calculation, and we chose for that a ring which has a fundamental mode at around 3.1 gigahertz. So that means this lambda is the circumference of the transmission line, and it's lambda at 3.1 gigahertz. And then we basically do this calculation for different angles. Okay, so what's plotted here on the x-axis is the relative angle between 2 qubits, and then this is the frequency at which we are calculating this. So remember that this is 1 lambda at 3.1 gigahertz. So obviously, depending on the frequency of consideration, the path lengths are quite different. So you can see that the coupling strength sort of shows this periodic fashion. So the color axis is shown here. It's 0 to 25 megahertz. That's the range here. And then you see that there is this periodicity, and then there are these bands of black region, which is basically 0 coupling. And then there are these bright regions towards the end, where you're actually getting close to the second harmonic of this thing. But right here in the middle, things look quite sort of nice and smooth. If you now take line cuts of this as a function of frequency at these different angles, which are spaced 30 degrees apart, then you get a much simpler behavior. And especially if you focus in the middle, where this yellow band is shown, what we call the special frequency. And this frequency is essentially halfway between the fundamental and the first harmonic. So at this particular value, and the couplings are shown at different relative angles in different colors, you see that there is one particular angle, 120 degrees, where the coupling is 0. Then you have 2 other values at 60 and 180 degrees, where the coupling is highest. And then the 3 other values at 30, 90, and 150, the coupling has some intermediate value and close to slightly lower than this maximum value. And so around this frequency, there are only 3 values. And then the relative variation of these coupling strengths as a function of frequency as you deviate, is relatively slow. but these ones vary faster, but this one is quite slow. So you have a little bit of room to keep your choose your qubit frequencies here. So this then means that if you space the qubits in this fashion at 30-degree intervals here in this particular thing, you get this system where every qubit can be coupled to 9 other qubits, and you have 2 points where it doesn't couple, so 120-degree and 180-degree. So what is actually happening? It's very simple to understand. At 120 degrees, the path lengths between one side, so between this path and that path, is exactly 180 degrees. So it cancels each other out. And for all other angles, you have different combinations, so the coupling strength varies up and down. But if you choose the spacing of your qubits, or basically the distance in wavelengths between qubits appropriately, then you can keep the variation quite simple. And now you start seeing the sort of the advantages of this design. It's very simple. It's a nice circular, uniform, symmetric layout. You have qubits going out in each direction, and yet the qubit. The really strange thing is that this qubit is more strongly coupled to this one as compared to the one which is right next to it, because the strongest coupling actually happens at 60 degrees and 180 degrees, and 30 degrees is the slight and is slightly smaller. And this is just because of the interference effect which you're having. And here that actually helps you stabilize the overall number of possible values of coupling you can choose. Of course, if you go choose all possible angles, then the variations will be a lot more. So you have to choose this carefully. And we decided to choose 30 degrees. So here is the design of the device. So it's actually machined in 3 different parts. And by the way, those who are familiar with superconducting architecture, this is what we call the 3D architecture, where the cavities are machined in 3 dimensions. But this is perfectly possible to do on the chip, just with microfabricated resonators. We are a fan of the 3D architecture because of its simplicity and modularity. So we decided to do this demonstration in 3D. So it's it's made in 3 parts, so you can assemble it quite nicely in a modular fashion. So here again, you see how the 3 parts look like. So here's the bottom part and the middle part, which contains these resonators, and then you place the chip, and then you close it up to make the full system. So it's also nice, compact, modular, and nicely sealed to protect it from radiation and noise. And you can maybe barely see these little holes on the top. That's where the measurement and control signals come in from. You put coaxial connectors on them, and that's where the signal comes in and out. So it also has a nice 3D integration as well, so you don't have to have wires crossing each other. Okay, and we wanted to, as the first experiment, the main goal was to really test this theory that does the coupling really vary in the way we had predicted. And for that, we chose to place only 4 qubits at cleverly chosen positions 1, 3, 9, and 10. And these were chosen because for just these 4 qubits, we can measure all the relative angles between them. That is 30, 60, 90, 120, 150, 180.
Excuse me, sorry to interrupt actually.
Yeah.
So this qubit coupling, what you are speaking of, is it the transverse coupling of this qubit excitations, or?
That's right, exactly. It's dipolar coupling again, yeah.
Okay, thank you.
Just mediated by this structure now.
So is it always like positive, like the way you are showing in the figures, or can it be tuned to the negative side also?
Let me actually see. I forget if this. Okay, so if you paid attention, the y-axis actually says absolute value of the coupling. So you are absolutely right. There are certain angles for which the sign will actually get reversed relative to the other. So of course, the signs only matter if you're talking about relative couplings between these two, but you're absolutely right that the signs are important. In fact, when we try to fit the data, we have to keep the signs in mind. Otherwise, and it's just simply the result of the phases, how the interference takes place between the relative angles. Yes.
Is it also possible to induce longitudinal couplings somehow through this architecture, or it's only radiative couplings which you can generate through microwave resonators?
Well, no, there are other ways of doing longitudinal couplings. In fact, that 3-qubit design I showed you there, the qubits are actually coupled via longitudinal coupling, which I guess in something we also call it cross-Kerr coupling. Here in this particular model of using the ring cavity, it's a mechanism to mediate dipolar interaction. But it's possible to imagine this. But this is also the most commonly used interaction form for these kind of systems.
Thank you.
Yeah, so so we chose 4 qubits so that we can keep the experiment simple and at the same time measure all the possible angles which we wanted to verify. So with these experiments, just like I described earlier, by bringing the qubits into resonance. So we chose the qubits to be slightly off resonant with each other when they are in their default state. And in this case, the Josephson junctions were also, we used only one of them. So they were not tunable by applying a flux. And if you actually pay attention, this is a completely made out of aluminum. There is no way to apply an external flux from outside because the superconductor will shield it. So we used actually an AC Stark shift tone to push the qubit frequencies by applying them locally on one of the qubits. And then we make them cross each other in frequency, and you get what you expect, like an avoided crossing. So this is basically spectroscopy. And you're seeing 2 lines corresponding to the 2 qubits as a function of some power of the Stark shift tone. So as we increase the power, the qubits move in frequency space, and then you get an achroid crossing. And from this, you basically get your coupling strength. So this was one way we did the experiment. Just to verify, there's another way you can get the experiment, is that even though the qubits are off resonant, they have some remnant coupling, which we actually call the cross-Kerr coupling. And what that means is that when you excite one qubit, it actually affects the frequency of the other qubit it is coupled to. And that we can extract, this frequency shift we can extract with a Ramsey type experiment, where we basically put the qubit in a superposition state and let it evolve and then accumulate the phase over a particular amount of time, and then with the other qubit in one or the other state. And that causes a change in the oscillation of this frequency. And from that also we can extract the coupling strength. And this is where the sign is important to make it fit with the data. And with these 2 techniques, we extracted all the coupling strength. So here we have actually shown the results with the correct sign here. So you can see that it's all positive up to 120 degrees. And then once you cross the 0, it becomes negative. And the 3 bars correspond to what we obtained from finite element simulations. So these are the calculations I showed you earlier. And the anti-crossing experiment and the cross-Kerr experiment. And you see that they match each other fairly well, and the coupling values have these 2 different finite numbers. So there's high value at 60 and 180, and then sort of a slightly intermediate value at 30, 90, and 150. So the
sorry, Vijay, just one question.
Yeah.
So the magnitude is let's say around 4 megahertz, the magnitude of coupling. This is in comparison to just some regular experiment where you can induce qubit-qubit coupling. This is about 10 times smaller or something? Or is there a reason?
No, not really. So this coupling is also within our control. We just chose it to be in the 4 to 5 megahertz regime. You will see it depends on what kind of experiments you're doing. If you're using the microwave activated gates, then this 4 or 5 megahertz is the typical scale one uses. If one is doing the frequency tuning method, then you can have a much stronger coupling if you want, like maybe up to, as you said, 30, 40 megahertz. The coupling strength value is actually not limited in this particular approach. It's just that we chose these numbers to work with. And you will see how, just in the next slide, how the coupling strengths actually can be controlled.
Okay, thanks.
So the small variation here is due to the manual placement of these chips, and then this of course can be improved better, but these are fairly small to affect create problems in real experiments. But in a more microfabricated and with more precision of placement of these qubits, you can do a much better job. So in fact, we sort of studied this, and this is what tells you how to control the qubit readout and qubit placement. So what you're seeing in this top right corner is a small section of where the qubit is placed. So on the right hand side are the measurement resonators, and on the left hand side is the part of the ring cavity. And this little qubit here has these 2 pads. This is like an antenna, and that's what gives you the coupling. So the size and shape of this antenna allows you to control the coupling. So by just making it longer and overlapping more with the fields in the bus cavity, you can make the coupling strength larger. I'm not sure if it is possible to make it 10 times larger. It might just become very big and cause other problems, but we can definitely go much higher than what we have shown here. And similarly, the coupling of the qubit to the readout cavity, which also sort of determines how quickly you can do the measurements and things like that, is also constrained. So we looked at this qubit readout coupling first as a function of the X and Y displacement. So we wanted to see if one makes some errors in the placement, how much variation you get. And then we sort of had this sweet spot here in the middle of around, I think 70 to 80 megahertz for the qubit readout coupling. And in the experiments, we got values in the range of, about 70, and then there was one particular qubit which we later on saw that had shifted quite a bit after the qubit was placed in the experiment. So the agreement was reasonable, and the variation is, it's obviously there, it's going to be present, but it's not too bad for it to be impractical, or that you have to require very careful tuning. And we did the same thing now for interqubit coupling as well. So now it depends on the positioning of the qubit, two of them, X and Y. And then you can see that this is the variation. Again, it's sort of here, it ranges from 0 to 25 megahertz. So on the extreme variation, of course, you can get much larger, but towards the middle, the variation is not so bad. And we had estimated coupling strengths of around 4 to 5 megahertz. Here for 180-degree position, the simulation showed about 4.9. Experimentally, we measured about 4.74 for this case. So this also was quite reasonable when compared to our predictions. So essentially, this shows how to control, and that this is a robust design for, and you don't have to worry about these things. So we also checked a few things. I will go through this very quickly. One is qubit crosstalk, and the point here is that if you're driving this qubit here, you could have some microwave leaking out to that qubit. I mean, this blue thing is not showing the path of the leakage. It's just saying that yes, you could have. And then what that means is that you will get some Rabi oscillations of this qubit because of this drive. And we were able to characterize this in great detail using basically by doing this experiment and then fitting all the evolutions of the qubits using Hamiltonian tomography, sort of described in the method described in this reference. And from that, we can basically separate out the parts. In fact, this method is actually a way to do the entangling gates. So we can separate out the good parts, which is the entangling operation, which is the ZX coupling term, as opposed to the other term, which is this crosstalk, which is this IX term. And we saw that the numbers we got were about an order of magnitude smaller than typical numbers which are obtained in this 2D architecture. And this is not necessarily a feature of the ring per se. It's more to do with the fact that in a 3D system, everything is nicely isolated. But it also reinforces the fact that by having qubits spaced out nicely and yet not lose the coupling strength, you can keep the leakage quite minimal. And you can understand that why leakage control is important, because you want to be able to drive the qubits without affecting other qubits when you are not indenting. So similarly, we also checked that the readout crosstalk is not there, which basically means that if I'm trying to measure this qubit, it should not accidentally measure other qubits. And there we essentially did it by looking at the Hahn echo experiment to look at excess dephasing due to the measurement in the present when the measurement tone is actually being kept on the other qubit, one pair we are studying. And we saw that there was at least 2 orders of magnitude suppression in the dephasing rates between the intended qubit and the unintended qubit. So that was also quite good and within practical regimes. So just to now wrap up, what we really want to do with is how do you extend this idea beyond, say, a single ring? And one particular thing is that, well, just make a larger ring. So here is now a larger ring in circumference, which means that for the same distance in units of lambda, the angles are now smaller, in this case 10 degrees now, as shown here, because it's roughly 3 times lower in frequency. And then you basically get the same type of behavior. But now we also realize that you don't want the qubits to be always strongly coupled. So what we're proposing is that we should introduce some kind of a tunable coupler, which allows the qubit to couple to the ring system or decouple. So it's a local control. So it's easy, it's scalable. It only goes as the extra overhead you need is is just as the number of qubits and not as some exponential or a larger, faster function of the number of qubits. And then you just turn on the couplers for the qubits you are interested in creating the interaction with. And that sort of helps you create a very flexible system. So in this system, it's just a scaling up of the idea. Now the qubits are spaced 10 degrees apart. But again, now every 1, 2, 3, 4th qubit will not be coupled because of the same reason. So now you get, again, 3 values of coupling: a high coupling region, an intermediate coupling, and a 0 coupling. And here in this 36 qubit systems, so 10 degrees spaced around 360 degrees, each qubit can be connected to 27 other qubits. Okay. And the price you pay here, however, is now this variation of the coupling strength as you move away from the special frequency is going to be a lot faster. And that sort of, you can imagine that now you have, you're working at much higher harmonics of the fundamental mode. So things are going to vary faster. So, but as long as your architecture doesn't require you to deviate too much from the choice of the frequency, which is possible if you have tunable couplers, then this still works. Another slightly more complicated but interesting idea is to now connect different rings together. And here we saw that if you connected the rings together, as shown here with a section of λ/2 transmission line with a characteristic impedance, which is Z/2, where Z is the characteristic impedance of the ring. And again, you connect the qubits with the tunable coupler, you can get very interesting networks with even more connectivity. So for example, in this case, you have a central ring with 6 qubits, and then you have 6 outer rings, each with 6 qubits placed 60 degrees apart. And in this case, this highlighted qubit which is on the outer ring is also connected to 27 other qubits, 3 within the same ring, and all the other 6 in all the other rings. So the intra-ring coupling is obviously much stronger. And then all the others, so what is amazing is that this qubit couples to every other qubit in the external, in the other rings with the same coupling strength at that particular point. And it does not couple to these 2 rings entirely because of they are spaced 120 degrees apart from the point at which this ring is connected. So the rings in the outside are connected to 27 other qubits, but the qubits on the outside rings are connected to 27 other qubits, but the qubits in the inside ring are actually connected to 39 other qubits. They're only not connected to the 120 degree qubits within their ring, and they are connected to every other qubit otherwise. So it's really a remarkable amount of connectivity that is possible for qubits which are far apart from each other, but in this nice symmetric fashion. And then you can basically use the couplings on it. So this is basically my last slide. And what we are really imagining is that you can now have this network of rings, and even the coupling between the rings, this λ/2 itself could be made tunable so that you can isolate the rings from each other. And when they're isolated, you can do operations on all of these rings independently without having to worry about crosstalk. So that now gives you the isolation. And then when you want to turn on an interaction between a particular pair of qubits in locations, you just turn on the couplers appropriately. Now, this number of couplers you will have to put will, of course, now not scale as favorably as the earlier idea. But because there are many qubits within a ring, this scaling is still going to be okay. And anyway, this is just sort of a cartoon version of how one could imagine. And then you can turn these couplings on, and you can connect qubits which are far off or qubits which are within each other, and really opens up a lot of flexibility. And it's completely compatible with all the standard practices which are done currently in superconducting qubits. So with that, let me conclude. I hope I've been able to show you and convince you that we have this really novel coupler design for long-range connectivity using a ring resonator. And it really exploits the physics of interference to give you these stable values of coupling with only little variation. And we were able to show that the numerical estimate of this interqubit coupling matches quite nicely with the experiments which we did in 3D circuit QED. But again, I want to emphasize that it's completely compatible to do it in a microfabricated way using 2D design. And it has very low micro crosstalk and some interesting extensions to larger network. So I'll stop there and take questions.
Okay, thank you, Rajamani. And it's time for questions and comments. So are there any questions, comments?
Hi, Vijay. I had
Yes, please.
Yeah, I had a question. Can you go back to your slide where you had the experimental setup with the spikes? Right, all the way. Yeah.
It's one, but maybe this is a better one. Yeah.
Yeah, this one.
Yeah.
So the thing is, so these spikes are basically for readout purposes, right?
Yes.
So my question is, suppose I sort of don't think of it as for readout purposes, I actually think of it as part of a system. Then what you seem to have is a very exotic James Cummings network, right? Because you have this qubit which is now coupled to a cavity mode or some mode, and then you're in a network. So you have a James Cummings network with all-to-all coupling. Or is this not the right way to think about it?
Well, yeah, I mean, the effective Hamiltonian can still be written as a James Cumming way. So what the readout resonators are here is basically another cavity coupled to each of the qubits. Now,
right,
you could actually imagine completely getting rid of the qubit, which is a nonlinear resonator, and you can just replace it with linear resonators if you like. And then it will be a method to create strongly connected harmonic oscillators. But that will only be interesting if we can turn the couplings on and off in some particular way. But that is, I think it's good you raised this question. I again wanted to emphasize is that this coupler really allows you the possibility of making all those connections. You don't have to always have them, and it does that in a planar architecture, that even things which are far off are actually still strongly connected. But the physics is the same. I mean, you can't really distinguish between what you call a readout cavity or a bus cavity. The couplings will be the same if you write down the Hamiltonian. But remember that here, this central bus resonator is a single resonator, but it's the physics, to describe its physics, which explains the coupling. It cannot be treated as a single mode oscillator, because the presence of the higher modes, the fact that there's a lower mode at 3 gigahertz and the next higher mode at 6 gigahertz, that's what gives rise to this coupling variation as a function of the angle. If you only keep one of the modes, then it will not reproduce that behavior. So one has to keep that in mind, but otherwise what you say is right. There's a lot more possibilities in terms of doing many body experiments in this system.
Right. Okay, thanks.
Is it selectively possible to inject photons into this bus resonator in this architecture? Or?
You're asking that, can I put photons in this bus resonator independently?
Yes.
Absolutely possible. In fact, in order to verify that our bus resonator has the right frequency, we actually do have that injection point. Let me see if it is possible to see here. Yeah, in fact, let me zoom in. This doesn't used to be possible. But you see this, there's a little hole here. That we brought another connector at that location to probe the cavity. So absolutely possible to inject any number of photons or do more crazy things with the bus resonator as well.
Something again connected to what Manas already asked. This spike-like structures, what are there attached to each of those transpond qubits?
Yeah.
So do they have well-resolved fundamental modes, or they are just like transmission lines?
So these are essentially what we call lambda by 4 resonators. It's a section of transmission line whose length is lambda by 4 at the resonant frequency. It is shorted at this end. So you see the central pin is connected to the ground. Okay. Here. And so that's basically like a short circuit. And on the other side, it's open because it's not shorted to the metal. So it's like an open closed pipe. If you want to take the acoustics example, that gives you a lambda by 4 resonator design. It just was the convenient choice for her, because now I don't have to worry about how to support the central pin. It's basically anchored on one end. Whereas this central ring here, I didn't talk about it, but you can sort of barely see there are actually 3 sapphire sort of stands underneath for it to be held on top of the ring. And in fact, we realized that placing only those 3 sapphire rings actually causes a slight distortion of the modes and makes the coupling slightly non-uniform. So if you don't want to break the symmetry, you have to put the like 12 of them to keep the overall symmetry identical. But that is all it is. It's a lambda by 4 resonator, so the harmonics are every 3x.
Okay, so that can be tuned in resonant with the qubit qubit frequency. Is it possible?
In this experiment, this length is fixed, of course, because it's this by design.
Okay.
But normally, what we typically do in this kind of experiments that we tune the qubit to be in resonance with this cavity. But it is possible to imagine more complicated versions of this where you have tunability in the cavity as well. It probably won't be in this 3D architecture, but in a microfabricated version, that's definitely possible.
Okay, thank you very much.
Yeah.
Okay, so any other questions? So if there's no question, also let's thank Rajamani again for his very nice talk.